This is the second seminar in the series of lectures, invited lectures on the modeling and simulation for additive manufacturing. And today it's with great pleasure that we are going to attend a seminar from Professor Julia Mergheim. The title of the seminar is going to be Multi-Scale Simulation of Selective Beam Melting Process Mesostructure and Properties. And just a brief introduction on our guest. Julia Mergheim is Professor for Applied Mechanics at the Friedrich Alexander Universität in Erlangen, Nuremberg, and she worked a lot on numerical methods on fracture and damage mechanics, material mechanics, homogenization, and she's nowadays an expert on the simulation of additive manufacturing processes. So she's really the perfect guest for our invited lecture. So Julia, thank you very much again for accepting our invitation. We are very, very happy to listen to you, and hopefully we could use the seminar for a discussion and start interaction, a deeper interaction between the different groups. So thank you very much for accepting the invitation, and Zoom floor is yours.
Yeah, thank you very much, Ferdinando, for the invitation and also for the introduction. So let me share my screen here. Okay, does that work?
Yes.
Okay.
Yes.
Perfect. Yeah, so the title of my talk today is the multi-scale simulation of selective beam melting, process mesostructure and material properties. And this work is joint work together with the PhD students, Christian Burkhardt, Andreas Kergasner, and Dominik Soldner from the Institute of Mechanics, and Johannes Köpf from the Institute of Material Science and Engineering for Metals. We work together in the Collaborative Research Center 814 at the Friedrich-Alexander-Universität Erlangen-Nuremberg. And that is why I would like to start with a short, let's say, introduction about the research center, which is named Additive Manufacturing. And it is focused on powder and beam-based additive manufacturing or selective beam melting processes of polymers and metals. So we have 4 different areas in this research center. The first one is powder and material design. Then we have controlled processes. The third one is simulation. And the fourth one, process analysis. And actually the objective is to produce multi-material or functionalized components by means of the selective beam melting processes. So we mainly work here in this area C, which is simulations. And I would like to introduce it a bit more details. So the aim here is that we simulate within this research area the different sub-processes which are there in the selective beam melting process. So for example, we have simulations for the powder material and the powder application process, but also thermomechanical simulations of the melting of the process itself. And one idea is, or one objective is that we try to predict the properties of the additive manufactured parts. So let's say, depending on the process strategy, mesoscopic simulations, homogenization, and optimization. So we want to have a kind of virtual lab. And since that is also, let's say, one of the object or the topic of my presentation today, I would like to look at that in more detail. So actually the vision is that we have, by means of simulations, such a closed simulation framework where we can produce optimized parts. So we have a topology and material optimization tool, which is done at one of the mathematic institutes at our university. By means of that, we can come up with the geometry, with the optimized geometry of the part, which is used as an input for the macroscopic simulation. The temperature, so the macroscopic simulation can predict the temperatures, also the stresses and the distortions. And the temperatures are used as an input for the mesoscopic simulation, which actually derives the grain structure evolution in the parts. And the grain structure is again used as an input for a homogenization framework with which we can then determine the macroscopic mechanical properties which go back to the optimization framework. So that is done as a collaboration between 3 different groups from mathematics, material science, and mechanics. So today I will mainly focus on the parts which are done here at the Institute of Mechanics. So that is on the one hand the macroscopic simulation and its coupling to the mesoscopic simulation. And then there will be a short part how to couple the mesoscopic simulation to computational homogenization, and that will again be discussed in more detail. So mainly these 2 parts. So that brings me to the outline of my presentation. So I would like to start with the introduction of the macroscopic thermomechanical simulation. So the governing equations, the discretization, and I will introduce a numerical study of the efficiency and the accuracy of the thermomechanical approach. So in terms of different numerical parameters and also some modeling assumptions. Then I will show how we can couple this macro simulation to the mesoscopic simulation of the grain structure. And furthermore, how the mesoscopic simulation of the grain structure can then be used as an input for the numerical homogenization framework to obtain finally the macroscopic properties of the additive manufactured material. So this last part, the numerical homogenization, will be discussed in more detail. So I will introduce a crystal plasticity model of the mesoscale on the mesoscale and how we can predict the elastic and plastic properties of additively manufactured Inconel. And I will end with some conclusions and an outlook. So additive manufacturing processes are of course quite complex, and therefore also for the macroscopic process simulation, there are different challenges. So for example, we have very high heating rates and temperature gradients, and these lead to residual stresses and also to distortions of the part. The challenge is that we have quite complex material behavior, so temperature dependent, and we also have phase transitions from powder to melt and back to solid, and which makes the simulation quite difficult or expensive is that we have within the process different time and length scales. So if we think about the time scales, let's say the process time could be several hours or even days. And if we think about how long it takes to scan a short line, so that is just in the range of milliseconds. And if we think about the length scale, so the component size is centimeter, but the beam radius is, let's say, 100 microns. So that is also on a different scale. And due to these different length scales, there are even on the macro scale various approaches for process simulations. So with the macroscopic scale, I mean that we model the powder by means of a continuum and that we do not resolve the particular powder particles. And in addition, we do not model explicitly, for example, the fluid flow in the melt pool. But even on this macro scale, we can distinguish what I call here lower fidelity approaches and medium fidelity approaches. So at the moment, only the lower fidelity approaches, which are computationally very efficient, are able to simulate really large parts and to, let's say, compute the distortions and the stresses within these additively manufactured parts. One example for such an approach is the inherent strain method, which was introduced in the last presentation by Professor Tu, and also its extension. Or we can have approaches with lumped layers where several layers are applied at the same time. So the advantage is, of course, that we are able to simulate these large parts. However, the predictive power is limited and depends on the particular geometry and the material and so on. So on the other hand, we have medium fidelity approaches where the scan lines are resolved. So that is shown here. Due to the different length scales, we still need to have adaptivity in space and time to be able to do, let's say, simulations at least of small parts and not only of single lines. The advantage is that we can predict with more detail, for example, the temperature fields, which are needed for the simulation of grain structures, for example, and also, let's say, compute stresses, distortions, plastic strains, and so on, which can be used on the one hand as a reference for the lower fidelity approaches, but also as an additional input for the approaches on a larger scale. So today I would like to introduce in the following our medium fidelity approach, and then also discuss its accuracy and efficiency. So here we have the governing equations. So we have a thermomechanical problem. So for the thermal problem, we solve the heat equation, and for the mechanical problem, the balance of linear momentum. So the heat equation is here given in terms of an enthalpy formulation. So H is the enthalpy. We have Q as a heat flux, and this capital Q here is a heat input by means of the laser beam. Heat conduction is governed by Fourier's law. So the conductivity is also temperature dependent, and we can have convection and radiation. We have to complete this equation by means of the heat input. So how that looks like, and initial and boundary conditions. So for the mechanical part, we solve the balance of linear momentum for the stresses. And we have the strains here, the total strain, which consists of elastic, viscoplastic, and thermal strains. And actually, the thermal strains are the only mechanical loads that we have here in this problem. So from the temperature, that is the loading that we have in the process. And the thermal strain is computed here by means of the heat expansion coefficient and the change in temperature. So here we need to complete that a material model and also boundary conditions. So I would like to proceed with the thermal simulation. So for the heat input, for the point heat input, we use here a standard Gaussian distribution for the volume energy. And let's say to make this simulation a bit more efficient, we can also integrate that in time. So if we want to apply larger time steps so that the beam does not jump from one point to the other, we apply a time integration of this heat input, which then results in a line heat input as it is shown here. The length of the line depends actually on the time step size, but we introduced this factor tau, which depends on the velocity, the radius, and the time step size. And we see if tau is 0.5, we resolve the movement of the point heat input. And if tau is equal to 12, then in a larger time step, the heat input is equal to such a line. Of course, there are some errors related to that, in particular in the maximum temperatures. So here we see the parameters we had before in the heat equation. So the enthalpy, which depends on temperature. So its derivative here is the heat capacity, and we see here this jump that is the latent heat for the phase change. And the conductivity is also temperature dependent. And for the powder material in green, we see that this is much lower. And then we have here in black the melt and the solid material. So due to these temperature dependencies, the heat equation becomes highly nonlinear. For the mechanical problem, we introduce a material model which should capture the influences of temperature, strain rate, and strain history. And therefore, we introduce a thermoelastoviscoplastic model. We have seen the kinematics before. So the stresses then depend only on the elastic strains. Here, the volumetric and deviatoric stresses, and some temperature-dependent material parameters, for example, the shear modulus or the bulk modulus. We also introduce some hardening in the plasticity model, which is governed by von Mises' yield function with isotropic hardening, which is given here. And the rate dependency, in particular for higher temperatures, is governed by a viscoplastic China type model, where we have here the evolution equations of the viscoplastic strains and the internal variable for the hardening. So we also implemented this model or the whole framework in a geometrically nonlinear formulation, where we used the logarithmic strain space formulation, which allows actually to use the same equations, but instead of the linearized strain here, we introduce the Henke strain, and then we need some pre-processing to the logarithmic strain space, and afterwards a post-processing of the stresses back to the real world. So we compared that later on with the solution of the small strain model. As I said, all the material parameters that we use here are temperature dependent. For example, we have here material parameters for the titanium alloy. The red crosses are experimental values from literature. And we then introduce some smooth functions to, let's say, that it's a bit easier for the numerics. For the Young's modulus here, for example, we see in black the Young's modulus of the solid material, which decreases with temperature. In green, we see the Young's modulus of the powder, where we assume in the simulation that the powder behaves linear elastic. So with just a smaller stiffness than the solid material. This red dashed line here, which is introduced, that represents the relaxation temperature, which is set here to 0.8 of the melting temperature. And whenever the current temperature is larger than the relaxation temperature, then the stresses and strains and internal variables of the last time step actually are set to 0. To make sure that, let's say, the stresses, if we come from the melt, are equal to 0. Okay. So by means of this temperature dependencies, also the mechanical problem becomes highly nonlinear. So as I mentioned before, we still have different length scales in our macroscopic approach, and therefore we apply here an adaptive discretization in space and in time. The adaptive discretization in space is done by the finite element method, and here we see an example how that looks like. So the elements are strongly refined in the region where the heat input takes place. And then they are coursing towards the boundary of the building chamber. And this refinement that uses hanging nodes, as can be seen here, and that is included in the DL2 finite element library, which is the basis here for our finite element simulation. The integration in time takes place by using a two-stage S-Diagonal-Kutta method, which is second order accurate, and has the advantage that it includes, let's say, an error measure, which we can use to adaptively change the time steps. So that is shown here in the diagram on the right-hand side. So we see as a time step size over the number of time steps. And let's say during melting, we need the small time step. If we wait until the next layer is applied or afterwards, the time step size is increased adaptively up to, let's say, from 10 to the power of -4 to 10 to the power of 0. So I would like to show first a small example of a thermal simulation of the selective laser melting process. The example is a pin, which is made of this titanium alloy, 5 millimeter diameter and 32 layers. And here we see how the scan strategy looks like and the temperature distribution during the process. We also compared the temperatures which were measured here below the plate in the simulation and the experiment. And well, actually, we had a few difficulties here with the initial conditions. We are working on that. But overall, the agreement is quite okay between experiment and simulations. So in the following, I would like to introduce a numerical study that we did for the thermomechanical simulation. Where we studied the influence of the mesh size and the element type, of the time step size, and also of some, let's say, modeling assumptions. So modeling of the surrounding powder, finite strain versus small strain, and the relaxation temperature on both the accuracy and the computational effort. And to do that, we use two different examples here. A small one, which is actually a wall, so a single line, which consists of 6 layers, where we tried out all the different possibilities, so different meshes, different time step sizes. And then we tried to identify an efficient, let's say, simulation setting, which is accurate enough, but let's say computationally more efficient than the reference solution. And we compared these two settings then for a larger example, which is given here below. So today I will only show the first 2 points here, the mesh size and the time step size. So we start with the mesh size and the element type. So actually we solve the thermomechanical problem in a staggered way. So for the thermal problem, we always use linear elements. For the mechanical problem, we use the same mesh, but let's say usually quadratic elements. However, we tried out here what happens when we use also linear elements for the mechanical problem. And we used 3 different mesh refinements. So all meshes are adaptive, but the minimum element size, as can be shown, as can be seen here in the pictures, is different. So for the refinement step 5, we see that is the finest one. We have a minimum element size of 12.5 microns. For R equals 4, we have 25 microns, well, roughly 6 elements over the melt pool width. We compared for these different meshes, and so overall we have 6 different settings here, so 3 different refinements and 2 different element types. We compare to start with the temperature, the Van Mises stress, and the displacement at this point A here, which is on the top of the first layer and in the middle of the wall. We see that the differences in temperatures are quite small. So only in the maximum temperatures, we see some, let's say, differences, but that's still okay. For the stresses, actually the same holds, only for the very coarse discretization, we see here small deviations, but let's say in the end, the stresses for all meshes are quite similar. The largest differences are actually obtained for the displacement. So here we see the displacements in Z direction over time. And we see that for the coarsest discretization, the displacement is quite far away from the reference solution. Afterwards, we had a look at the stress distribution. So here we see the Van Mises stresses in the middle of the wall. So we have here a cutting plane directly in the middle. On the right-hand side, we see the results for polynomial degree 2 and left polynomial degree 1. And at the top, we have the finest mesh, and then it's, let's say, getting coarser. We see that for the coarse meshes here with R equals 3, we lose these details in the stress distribution, which comes from the layer application. So that is kind of smoothed out by means of the discretization. So that is too coarse. However, the overall distribution here of the stresses and also the maximum stresses are quite similar for, let's say, these 4 different discretizations here. And let's say together with the results from the last slide and together with the efficiency, we decided to use later on here the linear elements with the refinement step 4, because the Van Mises stress, the error in point A was less than 1%. And if we compare the computational effort, so of this mesh here with the finest mesh with quadratic elements, then we only need less than 10% CPU time. Yeah, so the quadratic elements are, of course, very expensive. So then I come to the study of the time step sizes. So there we used 4 different time step sizes, which are denoted here by these 4 values of tau. So 0.5 means that we have the point heat input, and then we have here lines of different lengths. So let's say the real time here is 0.1 microns for the smallest time discretization, and it's 1 microsecond for the largest discretization in time. So again, we compare the temperature, stress, and displacements at this point A, and we see directly that here the differences are larger than in the study before for the different meshes. So in the temperatures, we see that in particular for tau equals 5, the maximum temperatures are not computed, but there is a very large error. However, the red and the black line, so for 0.5 and 1, they are quite close. The same holds for the stresses. If we look at the displacements, so the displacement in Z direction, that is also, I would say, still okay for all of them, but the displacement in Y direction, which is the scanning direction, so there we see very large differences between these different time step sizes. And also for the, let's say for tau equals 1, we already have a large deviation here from the reference solution for the displacement. So again, we also look at the Van Mises stress distribution in the middle of the wall. And here we see that for the coarse, let's say, time discretization for the large time steps, the stress distribution becomes wrong. For these 2, it's still okay. However, if we have a close look here for tau equals 1, we see the influence here of this line heat input. Yeah, we see the small differences. Well, that's not too bad. It's still okay. However, due to the large error in due to the large differences in displacements, which was larger than 25%, we decided to use tau equals 0.5 for the following study, so the smallest time step size. So that brings me to the large example. So here, as I said, we compare the reference solution and the more efficient solution, which was identified by means of the small example before. So that is the geometry, how it looks like. Here at the bottom, we see how the temperature and the Van Mises stresses evolve during the process, and also the scanning direction, the scan path, how that looks like. Now for the reference situation, we have here a finite strain model with the maximum refinement level 5, polynomial degree 2, and the smallest time step size. And the more efficient approach is for small strains, R equals, so the refinement level 4 and linear elements in the mechanical problem. And now, well, we hope that the errors are not too high. And again, we compared, let's say, temperature, stress, and displacements at one point over time, and also the distribution of the stresses. And we see that for the temperatures, well, that is okay. There are small errors in the maximum temperature, but it's, let's say, overall, it's fine. For the Van Mises stresses, well, actually, these results are quite new, so we have to study that in more detail. So we are not sure, exactly what is going on here in the middle. So there are larger deviations. However, if it comes to the end, so the stresses which remain in the part that are again quite equal, so there the differences are small. And what we see again in the displacements UY, which is the scanning direction here also, we see that there we have, let's say, the largest differences in the end between these two settings. If we look at the stress distribution, which is here within this plane, that's why we only see these two arms here of the geometry. We see that, let's say, the overall distribution of the stresses and the maximum values and so the place where the maximum value appears, that these are quite equal. However, we lose some of the details here. Yeah? So in particular, if we look here at the boundary, so then the stress distribution is slightly different. So that brings me to the conclusions of the study. So we have seen that a small time step is important to get the correct stresses and displacements. We use linear elements for the mechanical problem, and that is fine, and they are much more efficient. We need at least 6 elements per melt pool width. So that was this R equals 4, this refinement. So otherwise the stress distribution becomes wrong. And the displacements in scanning directions are the most sensitive to numerical errors here in our examples. So we also studied the modeling of the surrounding powder. I didn't show that here. That has a very large influence on the stresses and displacements. However, we have to study that further because this linear elastic assumption is also, of course, a simplification. And therefore, one has to be careful with the interpretation here of these results. And in the examples we studied here, the geometrically linear formulation seems to be sufficient. But of course, these are very small parts, so that can be different when one has larger parts or parts which have a different geometry. So now, as I mentioned in the beginning, it's not only the distortions and the stresses which depend on the temperature during the process, but it's also the mesostructure, the grain structure of the material. And that is the second part that I would like to discuss here. So how we can couple this macroscopic simulation of the process to a mesoscopic grain structure simulation. And then again, how to come from the grain structure to the material properties by using numerical homogenization. So as I said, so the mesostructure of the metals and the alloys depends on the building process. So in particular on the temperature gradients and on the temperature. And these, of course, depend on the, for example, the scan strategy. So here we see 2 examples from the Institute of Material Science. So we have here on the left-hand side a columnar grain structure where the grains are in vertical direction. And that is, I would say, the typical grain structure that is obtained in additive manufacturing. On the right-hand side, we see that by, let's say, changing the scanning strategy, we could also end up with an equiaxed grain structure. And that depends mainly on the temperatures. And therefore, the idea is now to use the temperatures from the macroscopic simulation as an input for the mesoscopic grain structure simulation. And that is how that looks like. So the macroscopic finite element simulation should be coupled to a cellular automaton simulation, which governs the grain evolution. The problem is that these two methods use different lengths and time scales. So here we see a picture how that looks like. So in blue, that is a finite element simulation area, which is, let's say, a large part of the building chamber. And this gray box here, that is the region where the cellular automaton simulation takes place. However, we can, of course, use the temperatures that are derived in the finite element simulation and interpolate them in space and in time to get the required temperatures in the middle of the CA, of the cellular automaton cells. In the CA simulation, the growing dendrite is mimicked by an octahedron, and it grows with a velocity that depends on the undercooling of the particular cell. And here, such a quadratic function is used where A is a parameter that can be chosen. And all the octahedra grow independently. So I would like to show a simulation result from this coupling. So the grain structure of a nickel alloy was simulated, which was built by the selective electron beam melting process. And here a cylinder with a diameter of 2.9 millimeter was simulated. So actually these grain structure simulation that happens at the Institute of Material Science and Engineering for Metals. Yeah, what we see here is a cut through the cylinder, and it is observed that in the middle of the cylinder we have this columnar grain structure, and the grains are vertically aligned with the building direction. However, here at the boundary we see that the grains are inclined, and that we also have some smaller grains here directly at the boundary. The same is actually observed here within these two vertical cuts at different heights here of the cylinder. So, and that is also compared with experimental results. And in the experiments here on the right-hand side, you see similar behavior. So we have these vertical grains in the middle and these inclined grains at the boundary. And also the grain size and, let's say, the grain shape look quite similar in experiments and simulations. In addition to these vertical cuts, we can also have a look at the horizontal cut through the cylinder, and that is shown here. On top, we have the simulation, at the bottom the experiment, and to compare the grain size, also quantitatively, we use here what is called intersection method. So we measure all the grains which are intersected by these white lines and average their size. And that is done at 5 different positions in the simulation and also in the experiments. And the result of that is shown here on the right-hand side. And there we see a similar trend for simulation and experiment. So the average grain diameter from the core, which is here in the middle, to the shell, which is outside, increases first to the transition region, and then it decreases even further so that we have the smallest grains here at the outside. The simulation always overestimates the results of the experiments a bit. And one reason for that is that the nucleation of grains is not included in the simulation, which is shown here. But still, there is a very good agreement of the simulation and the experimental results. So now the question is how this grain structure that we can, let's say, simulate and also see which comes out of the process influences the mechanical properties of the material. And that depends on the grain orientation, so on the texture, on the grain size, also on the grain boundaries. And we can compute the macroscopic properties by means of numerical homogenization. And therefore we use the grain structure, which is computed from the CA simulations as an input for the construction of the representative volume elements, which are needed for the numerical homogenization procedure. So here's a kind of overview how that looks like. So we have the selective beam melting process. From that, we can simulate the grain structure. Here we see on the left-hand side here at the bottom how this grain structure then looks like if we have, in this case, it's also a horizontal cut. And this has to be smoothed a bit to get representative volume elements, which can be used for the finite element simulation. But otherwise, we can directly take the shape and also the texture of the simulation, of the CA simulation, towards the finite element simulation. And then we do a numerical homogenization step and can have a look or can predict here the macroscopic properties. So that is the last part of my presentation. So how we can, let's say, compute or derive the properties of the additively manufactured, in this case, it's a nickel alloy. So I would like to introduce in the beginning the crystal plasticity model that we use on the mesoscale, and then introduce how we compute the elastic and the plastic properties of the additively manufactured material. So crystal plasticity is actually a material model which accounts for the anisotropy of the crystal structure. And in particular, if we think about the plastic deformation. So if we have the Inconel, that is an FCC, that has an FCC crystal structure, and the unit cell of that is depicted here at the top. And this FCC structure has 12 different slip systems. So one of the slip planes is indicated here in blue. And then the slip direction, that is this vector S here. And there are 12 different, let's say, vectors S that we can introduce here, which govern the plastic slips within this FCC crystal structure. And that is used in crystal plasticity. So plastic slips are only allowed along this slip systems. And then the plastic strain tensor is derived by the sum of these plastic slips, which is this gamma here. And the parameter alpha for FCC goes from 1 to 12. Yeah, so we have 12 different plastic slips multiplied with the Schmidt tensor, and that consists of the slip direction, and of M is the normal vector towards to the slip plane here. Plasticity in crystals is also always related with the movement of dislocations, and geometrically necessary dislocations are related to the gradient of the plastic slips. And in this continuum frameworks that we use, we do not introduce the particular dislocations, but we introduce dislocation densities. And they are related to the gradient of the plastic slips for edge dislocations, as is indicated here in the picture. That is a part of the gradient in the direction of the slip direction. And for the screw dislocations, the density is a part of the gradient of the plastic slip in the direction of the line vector. And these dislocation densities also enter the formulation, and therefore the model that we introduce here depends on the gradients of the plastic slips and is a gradient enhanced crystal plasticity model. So to solve this model, we need a set of equations, which is given here. So we have the balance equations, the standard balance of linear momentum. And in addition, we have here a balance of microforces, which has to be solved for each slip system. So in the balance of linear momentum, we have the standard Cauchy stress here, which is computed by means of the elastic strains and the elasticity tensor. And the elastic strains are computed by means of the plastic strains and the total strains. And the plastic strains were already introduced before. In the microforce balance, we have the Schmidt stress, which is a projection of the Cauchy stress to the particular slip direction, to a particular slip system by means of the Schmidt tensor. And furthermore, we have a vector and a scalar valued microstress. Here in this vector valued stress, we see that the dislocation densities and therefore the gradients of the plastic slips are taken into account. We introduce a flow rule here for the scalar microstress, which is actually a creep law. So the stress is defined by means of the rate of the plastic slip. And we use here this tangent hyperbolicus formulation. So that is just the regularization, which works best in the numerical framework. We introduce hardening. So the standard hardening here given by G alpha depends on the plastic slips. And we can introduce the self and latent hardening. And furthermore, we introduce some hardening factor here, which depends on the gradient of the Schmidt stresses. So we will see later that this enables us to model the whole patch effect so that we get a larger yield stress for smaller grains. In addition, we need some boundary conditions for the grains. So what we can have as the most simple conditions is micro hard, where the plastic slips are prescribed to be 0. So that would mimic a situation where we have a thin layer and a passivation layer here. So that is actually too hard for the situations that we have where one grain is next to another. And the softest boundary condition would be stress-free. So that would be, let's say, a situation where we have really a monocrystal like this one and no stresses on the boundary, which is actually not stiff enough. So therefore, we need a more detailed model, which is somewhere in between these two cases. And therefore, we introduce a grain boundary model, which actually depends on this Burgers tensor, which is the jump of the plastic strains which contains the jump of the plastic strains over the grain boundary. And then we introduce here a certain factor. In a bit, it's like a penalty. So we penalize the jump in the plastic strains. Yeah? And all the other quantities here are just of geometric nature and contain the different vectors here. So by means of that, we can compute forces at the grain boundary, which then enter the microforce balance. So now I would like to compare the results of these different grain boundary conditions by means of, let's say we have here a representative volume element, which mimics this columnar grain structure that is obtained in AM, and we apply a certain shear to that. And then we see here the equivalent plastic strains, dislocation densities, and Van Mises stresses. So we see here that the micro hard condition gives, well, 0 plastic strains on the grain boundary. That is not correct. The grain boundary model, as we can see, penalizes the jumps in the plastic strains from one grain to the other. And what can be observed here is that for the dislocation densities, we obtain here at these triple junctions, so where 3 grains meet, very high densities, which is also observed in experiments. The micro hard condition is also too stiff if we think about the stresses, which are much higher here than in the other 2 cases. So the stress gradient enhancement that I introduced, that enables us to model also size-dependent strengthening, so the Hall patch effect, which is introduced here. So we can choose different values for this length scale parameter L sigma, or equivalently, we could also change the size of the grain, so that would result in the same thing. And let's say the higher we choose this L sigma, then we see that, well, we also get a higher yield stress, which is what we want to have for, let's say, a smaller grain size. So we now use this model here to derive the macroscopic elastic properties and plastic properties of the additively manufactured Inconel material. And we always do that for 2 different settings. So on the left-hand side here, we see an artificially generated RVE. So where we just use the Voronoi tessellation here to come up with the grains, and also constructed the directions of the grains. So in building direction, and we have just, let's say, some small deviations. The second setting is that we use directly the outcome of the CA simulation. So here we see the grain shapes and also the pole figures, which describes the texture, the orientation of the grains, directly from the CA simulation, which looks a bit different. Here, these 2 figures above, that gives us the Young's modulus in different directions. So that is the building direction here. And we see that for this artificially generated structure, we get transversely isotropic behavior. The smallest Young's modulus is in building direction. The highest one is actually under 45 degrees. For the simulated grain structure, we see that we get similar values for the Young's modulus. However, the behavior is not transversely isotropic anymore, but we see a secondary anisotropy due to the scan directions, which were here in X and Y direction, so rotated by 90 degrees. And that can be observed then also in the Young's modulus, which is obtained here. So that comes mainly from the texture, so from the orientations of the grains, and not so much from the shape of the grains. Then we also compared the homogenized properties of the material with experimental results. And we see, so that is a tension test in the direction perpendicular to the columnar grains and in the direction of the columnar grains. And we see here that both the Young's modulus, the yield stress, and also the hardening a bit depends on the microstructure and on the texture. So for this direction here, we see that the Young's modulus is smaller than here, but actually the yield stress is higher. And that is captured quite well also by the representative volume element simulations. And finally, we obtained the plastic behavior of this material. So we identified the homogenized yield locus, so the yield function of the inconel, and also try to model that by means of a macroscopic yield function. We see here that we also get a highly anisotropic yield locus. On the left-hand side, again, for the generated grain structure, and on the right-hand side for the CA simulated grain structures. The differences between these two are quite small. However, we see that this corner here that is, well, not so sharp for the simulated grain structure, that is again the reason of this secondary anisotropy that we get due to the scan directions. The RVE size that we have here, which looks maybe quite small, is actually sufficient. We see here in red the average, and these dashed lines are the standard deviations for, I think in this case, 10 different representative volume elements. And we also changed the size of the RVE, and we have seen that the average value here does not change. Of course, the standard deviation changes a bit. So in this case, these 12 grains that we simulate here are enough. So that brings me to the conclusions of the homogenization part. So we successfully identified the macroscopic elastic and plastic properties of inconel 718 by means of numerical homogenization. The RVEs can be generated from the CA simulations. However, the macro properties, that is our experience, are mainly influenced by the texture and the grain size and not really the grain shape. So it could be easier to just use the pole figures here, but have an artificially generated, let's say by means of Voronoi tessellation, RVE, which does not capture the exact shape which comes out of the CA simulations. We capture here by means of the homogenization the anisotropies due to the scanning process, so in building direction and also in the scan directions, and the RVEs with the 12 grains are sufficiently large in this case. So that brings me to the end of my presentation. I've introduced a thermomechanical simulation framework for selective laser melting using an adaptive finite element discretization, and introduced a numerical study of the influences of different numerical parameters and also modeling assumptions. Introduced how to couple that macro simulation to a meso simulation, and again, let's say to a homogenization process to obtain material properties. And that homogenization was introduced in more detail. So the gradient enhanced crystal plasticity model on the mesoscale was discussed, and also the computation of the macroscopic properties. Thank you very much for your attention, and the DFG for financial support. Thank you.
Thank you very much, Julia. Really, thank you very much. So I would like to open now the presentation for questions or comments. I have a bunch of questions, but I would give preference to other people in the audience before I start with the long list of questions, which I usually have. Stefan, welcome, first of all, and please turn on the microphone.
Can you hear me now?
Yes, now we can hear you.
Super. No, I came late, so sorry for maybe asking something.
I noticed you were late.
I had lectures, you know. Working at the university is somehow still connected to giving these kind of lectures, so I can't attain. Anyways, but the thing is, Julia, I saw you made the point that it wasn't worth to go non-linear, geometrically non-linear in your models, right? I don't know the slide somehow in the first third of the talk. Now there is others in the community that say the opposite, and I'm indifferent to this, you know. I'm really interested in how, like, what are your reasons to come to this conclusion? Is the global deflection, is it? Because if you look at, anyways, maybe you can.
Actually, I was a bit careful here. That's so I did not show the results that we had here. So we compared the linear and the non-linear formulation As I mentioned before, we use as a nonlinear formulation a logarithmic strain space formulation where we actually use exactly the same material model and just bring that in the logarithmic strain space.
Mm-hmm.
And let's say for the parts that we simulated here, which are actually very small, the differences were, well, in the displacements, they were maybe the largest, but still very small. So much smaller than for the other things that I discussed here for the different time step sizes. But
I mean, the differences in the global deflections then.
There were differences in the displacements that were the largest ones, but still, I think not worth the computational effort, which is much higher. But I think that depends on the geometry of the part that you have, maybe also on the size of the part. So as I said, at the moment, we are here in the range of a few millimeters. So I think there it's maybe not so significant, the difference.
Yeah, well, I'm very happy if we get away with linear computations. I'm really happy about that. I was just imagining, you know, that when you have very large volumetric strains, because you have large temperature differences, then you would need to go really into the large strain formulation. I think that's the usual argument, but you didn't see these problems, did you?
Well, as I said, so we still maybe have to look into that in more detail, but for the cases that we until now simulated, we didn't see these large differences.
Usually so actually, then somehow these formulations become unstable, maybe if the strain is too large or so. But yeah.
Yeah. Well, I think so. Actually, I like large strain formulations, and I was more in the other direction than you to start with, and thought, okay, we need that definitely. But I think there are, of course, also differences in the large strain models that you can apply, and maybe one really has to look in more detail. So I think that in general, so my opinion has been that we need large strains, but from the simulations that we did until now, the differences were small.
Okay, thanks. I'll leave it at that. Thank you, Julia.
Yeah.
Julia, do you have an assumptions in these logarithmic strain models? It's an isotropic or
So the model is isotropic. So what we used here? Yeah.
Okay. So that's the reason, because you go to the logarithmic strain. Okay. There is also a question from Juan Alvarez Naranjo. Please.
Hello, everybody. Can you hear me?
Yes, sure.
Perfect. Hello, Julia. Thank you for the presentation. It was really engaging. I have two questions. The first one is related to the calibration step. I have seen in the presentation that you calibrate several parameters which depends on temperature. How many parameters do you need to calibrate in the simulation?
Did I understand that correct? So how many parameters are in the complete model?
Yes. For example, to simulate one sintering process, how many parameters do you need to set?
Okay, so let's say in the in the thermal model, we have the conductivity. So all of them are temperature dependent. That makes it a bit difficult. So you have to define these functions here, which depend on temperature. Well, these are the parameters that we need. Of course, this relaxation temperature is also a parameter, which is not directly given. Yeah, which you can choose. Yeah, what else? Yeah, the heat conductivity. So is that what you mean, or maybe I didn't get that?
Yeah, the question is when we are doing the simulations, we need to set certain parameters which varies, depends on, for example, in this case, temperatures, and other parameters can keep constant or can just put in the simulations as a constant values. So I can see here, for example, you need to calibrate several parameters which are dependent on temperature. And but yes, the question is how many parameters do you need to set, which depends on temperature.
So maybe I don't understand it. So do you mean parameters which define now these temperature dependent functions? But that, so we just put that in, so we didn't change that then afterwards with respect to the simulations.
Okay. And yes, and it's because, for example, in the additive manufacturing process, it's really common to recycle powder. And of course, with recycled powder, the properties of the material is degraded. And is how can we track the degradation process of the materials, and which parameters do you need to analyze in order to reproduce an approximation between the process and the simulation?
Well, actually, I don't know. So I know, so there are other works in our research center, so mainly on polymers, where the degradation of the powder was really studied. So experimentally and also numerically. But here for the metal powders, actually, I don't know what you would have to change to. So let's say if you have the old powder, so which properties you would have to change to take that into account. So sorry, I don't know.
Yeah, this is a good point. I mean, I think it's very uncommon that people take into account this aspect. There are so many uncertainties in the whole process and simulations that, but you know, the point is for sure is a good point. Okay, thank you very much. Let's move to Kanayas. I mean, he has also a question.
Yes.
Ken?
Thank you. Thank you for the interesting presentation. First of all, I want to follow up on the geometrical nonlinearity. Well, I was also a bit intrigued about that. One thing, if I understood you correctly, is that if either when you're doing geometrical linear or nonlinear calculations, I think you're making use of the additive decomposition of the strain. And is it a valid assumption when you're doing the geometrical nonlinear calculations? If you would use a multiplicative decomposition, maybe the discrepancy between the simulations would be a little bit more?
So let's say, of course, I know that usually you have for finite strain plasticity the multiplicative decomposition of the deformation gradient. However, there is a model so that was introduced here by Mia and also others afterwards, where you use a logarithmic strain space. It means you use the Henke strain, which is the logarithmic of the right Cauchy green, so of C, this F transpose F. Yeah, the logarithm of that. Mm-hmm. And you can show that if you put that in, then due to this logarithmic formulation, you can also use this additive decomposition. So actually this epsilon is then not the linearized strain anymore, but that becomes this Henke strain, so this logarithmic strain. You have to, what you have to do is that you get out the C, yeah, from your finite strain simulation, this F transpose F. Then you do a transformation of that to the logarithmic strain space. Then you get out this logarithmic strain. With that, you go to the material model. And in the end, the stress that you get out, you have to transfer that back to the, let's say, real world. It was shown by several, let's say, people that you get similar results for the logarithmic strain space model as for the multiplicative decomposition of the deformation gradient, unless the shear strains become too large. But if we speak of large, we speak of, I don't know, 100, 200%. Yeah, so that is not in the region of 10 or 20 or 50, but really large. So then you get a problem with the logarithmic strain formulation, because then you introduce some artificial softening, which you don't want to have. Yeah, so that is the only problem. Otherwise, and that's why we decided to use it here. It is equivalent to the multiplicative decomposition. And in this case, of course, well, actually that was the easiest way to go from the small strain to the finite strain model, because the material model has exactly the same structure. Yeah, and you only have some kind of pre-processing and post-processing step afterwards.
Okay, thank you.
Yeah.
So thank you very much. There is also a question from Olfa D'Angelo.
Yeah, hi, thank you. Yeah, I have two questions. One is more on...
What a beautiful background.
Yeah, right. It's a new Zoom background. It's
It doesn't look like a Zoom background, but that's fine.
Thank you. Yes, so I was wondering, first of all, you mentioned that you use a continuum model for powder. So I assume you basically don't care at all about the material deposition.
Well, the layers are deposited, but we don't care about the powder and, let's say, the density of that, or so we just apply, let's say, some layers of elements. Yeah, okay. Exactly.
Okay, and so then you also give Young's modulus of the powder. I think it's a green line in one of your spreadsheets. Yes, and what? So is this some sort of effective Young's modulus, or how do you find that? How do you make that up?
But that is actually a quite simplified assumption, so that we assume that the powder is linear elastic. So it's quite common in literature also, because that's the easiest way. But actually, of course, it is wrong, because if you think about it, then you could also the powder would also have a certain stiffness if you pull on it. Yeah, which it does not have. Yeah, so actually you would need also a plasticity model for the powder and model that in more detail, but that makes the simulation, well, quite unstable to do that. And therefore this assumption is the easiest one, to assume it's linear elastic. But, well, I didn't show the results in detail, but we did some tests on that. And because it is also one idea, let's say, which is done in literature, to omit the powder in the mechanical simulation. So to just leave out the powder completely. And well, actually, we found quite large differences. So depending on how the powder is modeled. So depending on the Young's modulus, if you assume if it's linear elastic, and also depending on the amount of powder that you take into account in the process. So that influences the displacements strongly, but also the stresses. Yeah, but it's true. So this linear elasticity, so that's just, a number. So it's not something that we homogenized. So it's just a guess.
Okay, thank you.
Okay, thank you.
Then
Okay.
maybe I can ask another small question. Thank you. Which is more on the future, and how such simulation could be coupled. And do you think it could be coupled with, like, let's say, in situ probing, for example, on the temperature gradient during cooling, to then have a more close to reality prediction of the granular structure in a 3D printed part, like sort of have a live prediction?
So sorry, again, what do you want to couple? So the macro simulation with what?
Yeah, no, the simulation with probing the temperature during cooling, probed in situ during the real process. So basically coupling experiment with the type of simulation you propose to be able to, for example, detect right away large temperature gradients or large defects in a part. So do you think this is something realistic? Is it something like science fictional, or what's your...
Well, it would be nice. So actually we did some work in the past on some reduced models for additive manufacturing, which would go in this direction. But so we were not really successful with that because it's not really a situation which can be where you can find something like a reduced model quite easily, which could then be used, let's say, as some kind of real-time simulation. I think that's what you mean, so that you can run that, let's say, the same time as the process. Yeah, but I think I think there are so many people now working on additive manufacturing, so I think it should be possible in the future to do that.
One day will be possible. Let's see.
Thank you.
Okay, thank you very much. And let's move to Zhang Yancheng. He has also questions.
Yes. Sorry, there's a video. Okay, it's open. Thanks a lot, Julia. Very nice presentation. And my question is mainly about for the part of crystal plasticity. You can hear me? Yes, actually, when you give the first curve about to get the stress strain curve based on when compared to experiment, the first curve, I think, yes, maybe previous one, yes, maybe this one. When you get the macro structure, grain structure from experiment, here we use almost the 2D grain structure. It's not really 3D, but in really experiment, normally it's 3D grain structures. Do you think it's the influence is bigger or not?
Well, it's true that we use actually something like a 2D grain structure in the way that we only elongate the grains in the third direction. Yeah, so they do not change size. But actually, actually, I think that, let's say, what we found out is that, at least for these elongated grains, so the actual shape of the grains does not have such a large influence on the macroscopic properties, but mainly the texture, so mainly the orientation distribution. And therefore, I think it would not change the picture so much if you change, let's say, if you still have columnar grains, but let's say some of them end in the middle and others start somewhere. So, well, we didn't try that actually, so it's just a guess, but due to the experience that for these simulations, if you only change the shape of the grains, but keeps the same texture, we get quite similar results. So therefore, I think it might not lead to very large differences.
Yes, and also here, I didn't quite understand. Here is you validate your model or you calibrate your model. This is my question. If you calibrate your model, it doesn't matter. If you want to validate your model based on your obtained input parameter from literature, so this is maybe a problem.
Well, actually, I don't remember exactly how that was. I think maybe one of the directions was used for the calibration and the other for the validation. But so I think that was how it worked. Yeah, but I'm not sure exactly. But yeah, it's true. So we used, of course, one of the results to calibrate some of the parameters on the micro scale, and then use the other one to validate it.
Okay. So, and also continue still about this one. The temperature you for the experiment is at the room temperature of or at a relative high temperature because the state is quite different. At the room temperature, I think the residual stress will have a great influence for the traction curve. At high temperature, it's less influence. I don't know, in your case here, you presented.
Well, these experiments are at room temperature. So what did you say? What has a high influence at room temperature?
Yeah, at room temperature, normally from this kind of process, usually they have residual stress. They will produce the residual stress. It's usually at the initial state before we do traction test. Initial stress is not very not very clean. Usually there's a residual stress correspond followed with. I don't know my question is clear or not.
Well, we didn't account here for the residual stresses. That is missing because actually we did not introduce any residual stresses to start with.
But the results are already quite nice. Thank you very much. I don't know, could I still ask your one question about the large scale model for the macro scale model? Could I have a different question? Yes, when I saw it, it's a model, the mesh, there's adapted mesh during the simulation. I don't know for the whole, the calculation time for the whole calculation, I don't know the portion of the mesh adaptation, it's take also very costly or not compared to resolve the mechanical problem. It's
well, actually, I cannot give you any time now. I don't know exactly how much it takes, but actually that is the advantage, in my opinion, to use this DL2 library. So that is quite optimized in this sense. So that is one of the, let's say, properties or the nice functions of this DL2 library, that this adaptivity with the hanging nodes and the structure which is needed to refine and to coarsen and so on. So that is provided by the library. So we do not do that ourselves. And I think therefore it does not take so much time here. Of course, what we need to do in the mechanical problem is also to project the internal variables. So if we refine and coarsen, so that of course also takes some time, but it's still, in my opinion, necessary and faster than not using an adaptive discretization.
Okay, thanks a lot. Maybe last questions.
Quick one.
Could I ask, sorry, could I ask the last one question?
Sure, quick.
Yeah, when you do the sensitivity analysis for the displacement or distortion in the y direction, in the z direction is quite nice, but in the y direction, there's a big difference. Could you give us some idea about the potential, what's the main reason, and also how, when we want to do the following test, how we choose the reference model? If the displacement, the variation is so big, how we choose the reference models or benchmark models?
Well, what we observed was that always, let's say, this y direction, that is the scanning direction, and there the difference was the highest. In particular, if we have, let me go to that, I think the different time steps. Yeah, exactly. And that comes mainly from this line heat input. So that, let's say, here's a time step size. So by means of this tau, well, we cannot increase the time step size without integrating the heat input in time. And therefore, that always means that it's not only actually the time step size, but also the heat input is a bit different. Yeah, if we do that. And this difference in the scanning direction, I think that comes from the fact that then you introduce, let's say, that the material which melts and where the highest temperature is, so that looks a bit different at the point where you, well, at the point in time where you scan. Yeah, and that is also, I think, this line heat input, that is also the reason that we see that in y direction in particular. Yeah, because this line is also in y direction.
Yes, it means the energy, I would say the energy length is too big. The length of energy, it's maybe strongly influenced. Okay.
Exactly. Yeah.
That's a lot. Very nice work. That's a lot.
Thank you.
Let me come to a couple of questions, quick questions also from my side. One, I noticed that you're working with DIL2. Do you have any problem with the fact that you cannot use tetrahedral mesh, or or also the meshing, you know, for complex geometry. So what was your general impression of the tool? Because we tried to use it for other problems, not for additive manufacturing, but the end of the story was not so easy. What is your...
Well, that is true. So we also use that for in several other projects, but there are also projects where this limitation that you can only have hex elements, where this is really a big problem. Well, I think at the moment they are working on the extension to also have TEDs, so we are hoping for that. But for the additive manufacturing, well, the reason might be that we mainly simulate small parts and simple geometry. So at the moment, we do not have any problems with that. Okay. Yeah, so the decision was more on this adaptive discretization. So based on that, so that it is very efficient and fast. And it's parallel, yeah. It's parallel, so that so actually it really works well. But yeah, of course, so if it comes to more complex geometries, that is really difficult, and we did not find until now so a nice meshing tool which can really do nice hex meshes. So we tried out some of them, also open source, but also commercial ones.
No, I know.
It's complicated.
Yes, exactly. And really the last question, you showed the simulation of the pin where you had a comparison with experiments and simulations, and there was some mismatch.
Yes.
So it's just some complex, is due to some experimental issues, or it's some physics that is missing in the simulation? What is your feeling?
So my feeling is that was more let's say a communication problem between.
No, that's very possible.
Yeah, but we are working on that. I was also, well, I asked myself whether I should show that or not, but then I thought, okay, actually we discussed about the setting in the beginning, but then there were some differences, and therefore, well, we are doing that, or we are redoing that, but I think it's not something important which is missing.
Okay. Now we all know, I guess, all the difficulties with all these aspects. So don't worry, that we appreciate the overall contribution. So thank you very much. Really, Julia, I think, again, thank you very much for the time you spent with us, for the presentation, and on the